So yeah, welcome everyone to Paper Club again. Today we're going to be talking about another paper which is still under review at for iClear 2021, which is about Lambda networks. And I'll just share my screen. Okay. Cool. So Lambda networks are an interesting new approach to attention. Basically, they're trying, the main contribution that the authors are making is to propose a new type of layer for machine learning models, which is capable of capturing long-range interactions without having to use these very expensive attention maps. So the main claims here are basically two claims. One, that they can do very efficient, they can capture long-range interactions with very efficiently memory-wise. So they don't actually make the claim for time because their algorithm is still in time. It's still very expensive unless they restrict their attention, which sort of brings the whole thing down, because then you don't capture long-range interactions, just short-range interactions. Yeah, and wait, there were two claims. Oh yeah, and the second claim is, yeah, of course, that you don't need attention. So capturing long-range interactions with low memory, and then not needing attention, at least not in the traditional sense of attention. I just need the chat. Okay. Okay. So there are a couple of extra resources. So because this is very it's very related to attention, I have here handy the Attention is All You Need paper, in case we have any questions about that. And there are a few implementations. I'll link. There are a couple other things that you can check. So first, there is an implementation of Lambda networks in PyTorch, and it is literally this long. So yeah, you can go check that out and see if you can use it. So this is the Lambda layer, and a Lambda network is just stacking them up. And if you go to Yannick Kilcher's YouTube channel, he has a video on Lambda networks, and he does a really good job at explaining them as well. So please do go there and check it out. And just for fun, we're going to be comparing with the vision transformer, which we presented a couple weeks ago in Paper Club. If you weren't here for that presentation, this is basically a proposition also on the review for iClear 2021 on how to use transformers in images, and we'll see why that is a challenge in just a moment. So yeah, so that sets up our scene for the paper. So on a very high level view, what this paper is trying to do is to solve the problem with attention maps, and they show the problem here very well in this image. So basically, if you have an image and you want to find a transformation for this pixel that is going to work for your network and from which your network is going to be able to learn, an attention map, if you call this your attention context, so this is how long you will be how far you will be attending to, you basically need to learn a weight for each pixel. You need to learn a weight for each of the surrounding pixels, which means that you have all these attention maps, which can become prohibitively expensive. So you can see how this explodes in memory. What Lambda layers claim to do is that you have a fixed size of attention map, and you apply the same attention map to every pixel. So you just learn some relevant features about the context, and then you apply the same features to every pixel. So I have a few diagrams here, which we can help to navigate the paper. If you read it and did not get the whole thing, you're not alone. The notation gets very tricky. So let's just walk really quickly through what is happening in the paper. So we can sorry, we can start with just saying what attention is doing and a little bit on the intuition on why attention learns and what exactly attention is learning. So attention starts with your input sequences. So I'm going to put in brackets the dimensions just so that we can follow up where memory starts exploding and where are the key areas where we need to improve. So this is your input sequence, and you have a context. Now, n will be the number of input sequences. The number of input sequences that you have, and d is the length of your sequence. So if this was a sentence, then d would be the number of words in the sentence, and n would be the number of sentences in your training algorithm that you want to process at once. And same with your context. If you have a context of different size to your input, then that context is going to be of size m. So if you have a pixel, then m might be 5 or 6 surrounding pixels. And again, just for simplicity, let's assume that the dimension of the context is going to be the same dimension of x, of your input. If you go to self-attention, then the context is the input, so it becomes simpler. And in the context,
might that not be a bit misleading? I think if d is the number of words, right? So d should be a constant, right? So you probably assume that we have like some sort of padding or so.
Yeah. So d is your sequence length. So it could be the number of words.
I always thought that n was the length of your your sort of sequence thing. Because that's a position, because also it's the position in your things. Yeah, it's, I know it. So, D might be like an embedding, right? D might be the embedding of words, so it has a non-zero dimension.
Oh yeah, that's it. Yeah, sorry. Yeah, sorry about that. Yeah. So sorry, n would be the length of your sequence length. Yeah, because then we add the batch size on the left. So yeah, n is your sequence length. Sorry about that. And d is your embedding size. Cool. Same with the context. M is the length of your context, and d is going to be the dimension of your embedding. So okay, sorry about that. But okay, so what happens when you do attention is you compute. So you do a linear mapping of your inputs to get your queries, and the intuition behind this is that you want to get some weights that learn only the important features of X, or learn to say what features you should learn from X, and you get your queries. And the query key value notation is going to become clear in just a moment. But same for the context. So for the context, you apply a linear mapping, and it gives you your keys and your values. Now, in the most generic version of attention, you can actually have your values come from something other than your context. But normally, so for image processing and text processing, your context is usually gives you your keys and your values. So what does attention try to do? Attention tries to learn a nonlinear relationship between your queries and your keys, which intuitively is going to say, well, if you have a certain feature in your query and a certain feature in a position of your context, then you should pay attention to this point of your values. So this is what we call the attention map. And we'll get back to the attention map in a second, but the attention map is basically saying, so if you imagine that your k dimensions, or your reduction in dimensions, is going to be for an image is going to be like pixel colors, if it has corners, if it has if it has some texture, whatever. So whatever the model learns from it, you will be able to. So what this nonlinear relationship is going to say is that, well, if a pixel here is red and a pixel in the context is green, then you should pay a lot of attention to that pixel. or if this pixel is in a corner and this pixel is also in a corner, then don't pay any attention. So that's where this attention map comes in, and the attention map is going to give you a value for every element in your input sequence and every element in your context. So that's that's what the attention is going to do. And then you apply that attention map on your values, which also come on the from the context, and that gives you your output vector. So it transforms a set of inputs and a context into a vector that then you can use to say whether a pixel belongs to an object, or whether a pixel or whether a word is part of is the subject or part of the object, and so on. So this is the idea of attention. Now, what is the big issue with attention, and in particular with self-attention, is this guy here, because this n by m can become very prohibitive, especially if you are working with images. Now, we said before that n was the length of your sequence, right? So if you think about images, if you have a 100 by 100 image, then the length of your sequence is 10,000. And if you have 3 channels, then you have 10,000 by 3. And then if you want to do self-attention, which can be seen as a global context, so it's your long-range attention, then this also becomes 10,000 by 3, which means that this matrix is 10,000 by 10,000. On top of that, you have to add the batch. So if you want to process more than one matrix, more than one example at a time, your batch dimension gets propagated everywhere, and having to store this in memory for every batch that you are storing becomes quite computationally prohibitive, especially on the memory axis. So what this paper is trying to do is, well, how can we come up with a layer that does the same thing that attention does, but doesn't require us to store matrices of this size? Now, I'm going to drop the batch notation just for simplicity, but we'll get to it later. So what they propose is something they call Lambda Layers, and Lambda Layers they start with the same concept of attention. So you have your queries, your keys, and your values. But now instead of computing this mapping, so these relationships between the queries and the keys, they say, okay, let's just compute a nonlinear relationship or learn a nonlinear relationship between the context and the weights and the learnable weights. And the intuition behind this is that you will learn how the context is important on its own, independent of the queries. So you're just looking at, let's call it self-attention between the pixels, so between the context. So you're learning these sets of features just for the context. And then you multiply that by the value. So you see, we are skipping the combination with the queries. We say we don't care that so we don't need to learn relationships between the queries and the keys. You just need to learn the right content information, and then apply that directly to the values. And that is what they call the content lambda. So this is one of the first lambda functions. And what you can see here is that this does not depend on the dimension of your queries. So you can apply the same content lambda to every query. And what they claim in the paper is that if you learn this properly, then you can capture all these long range dependencies. Now, I don't know if it's because they tried it and didn't work, but they realized that. So of course, this doesn't capture position. This only captures the content. So it doesn't. If you have a global context and you multiply this by your queries, you have no idea where your query is with respect to your features, to your context features. So I guess they tried it and it didn't work. So they decided, well, we actually do need some positional embedding. So they came up with this position encoding. So it's of size n by m, meaning that for every element in your query and every element in your context, you have an encoding or an embedding, which is a vector of size k, that says how they should be related. And you learn that through the value. So you multiply it by the values, and you have one vector of size k times v for every one of your input elements in your sequence. Now, this may seem a bit counterintuitive because they were trying to get rid of this, and they didn't, because it appears here again. So this is going to be a very large matrix. But what is important here is that this is fixed. So it is a set of learned encodings, and they don't depend on the batch. So the same encoding is applied to every example. So in reality, you only need to store this. You only need to store one of these matrices, and instead, in attention, if you remember, you need to store B of these matrices, where B is the batch size.
One quick question. You say it has to be stored, right? But if it depends on n and m, which are the relative positions of your queries, and so it probably depends a little bit on what the positions are. But wouldn't you expect that if a new batch comes in, the positions in those batches are dissimilar, or is it purely just like an integer position, like it's on the first position, second position, or third position, something like that? Know what I mean?
Yeah. So so of course all the images are of the same size. All the images that you're processing are of the same size.
Yeah.
So what this encoding is doing is encoding purely the importance of position. So they are splitting attention between position and content, and where content is this thing here. And this encodes purely position. So it doesn't really care about the features that you have in your input.
Yeah.
It just learns to encode, well, if you are on the top left corner and you are attending to the bottom right corner, maybe they're not very important.
Yeah. So in principle, we could replace this by a more traditional kernel function, right? Like a Gaussian square.
Yeah. So indeed, they replace it later by a convolution. So they apply a little trick so that if you want to do a global attention or a global content capturing, this becomes n squared times k. Later in the paper, they argue that, well, still there's a big inductive bias from locality, so you can actually relax this by zeroing out a bunch of elements in this position encoding, and then they implement a convolution to do that. So it's a learnable kernel.
They make it linear by sort of broadcasting it out into a matrix, right? But it wouldn't have to be a matrix per se. It could be some complicated function. Okay, thanks.
Yep. Yeah, indeed. Cool. So now we have our position lambda, which captures just these relationships between, well, let's call it pixels, because this is very focused on applying to images. So again, if n is all your pixels indexed and m is all your context indexed, then you have how you should attend to each of the pixels, and that's applied to the values as well to get your position lambda. And again, what's important here is that neither of these depend on the batch. So they are always the same transformations applied to every batch. And of course, they change the learnable weights. So there is something to learn here. But you don't need to create one of these massive matrices for every batch, which is one of the main memory bottlenecks in attention mechanisms. And then Well, then you do a multiplication and reduction. So this one is broadcast on every pixel, because as we said before, the content is translation invariant. So you apply the same content lambda to every pixel, and you get your what they call the lambda encoding, and you multiply it and you get something of the same size as your previous attention. So if you see, so if you do a bit of looking into the indices and so on, and I'm not going to go through everything, you will see that this n times m only appears here, and in that context, it only needs to be done. It only needs to be done once, so you don't need to recompute it for every batch. So in that sense, it is a lot more memory efficient, and we'll see in the results, they show that they can actually improve accuracy by reformulating attention in this way. Yeah, so the batch appears here, of course, and here, and it will appear here again. But all these expensive matrix calculations will not contain the batch, which is a huge improvement. We'll see later in the complexity results. But also, if you see the inner dimension is playing a big role here. So as long as you can manage to keep this inner dimension small, and then they make the values the same dimension as k and so on, you can actually keep this on a very tight memory. So this is usually about 16 or 8. So you can keep it very tight. So that is, in a nutshell, what Lambda layers do. Are there questions about the Lambda layers, how they relate to attention? Is that clear? Okay. So I'm going to assume that's a yes. And so let's get a bit onto what they actually have to do an extra step to improve the complexity. Oh yeah, so in this paper, there is a lot of confusion with indices. So I would recommend, if you're reading through a paper, just take it a bit slow and make sure that you follow all the indices, because they do all these reductions, some reductions on dimensions, and so yeah, so just be careful with all the indices if you're implementing it yourself. So yeah, there's this this trick that you can do with if you want to just use locality. So if you don't want to do the global context, which in my opinion defeats a bit the title of the paper, because they make this especially for long range dependencies, and if you get a local context, then well, they're not long range dependencies anymore. But anyway, if you want to use locality as an inductive bias, you can also formulate the problem as a convolution, and then this becomes a lot faster than doing the matrix multiplications. Okay, so before we get into the complexity, there is still a bit of a trick that they do, which is that they define this multi-head, well, they call it multi-query lambda, which is a bit of an equivalent to multi-headed attention. It's actually not an equivalent. It is similar, but it is not equivalent, where they say, okay, you don't need to apply one lambda for every query. So if we go back to our diagram, you see that this lambda is going to be computed for every query. You're going to have one pass, and you have to learn the new lambda weights. So all the weights and the lambda is going to be it's going to be different for each one. They say, well, instead of computing one lambda for every query, compute lambdas for batches of queries, and then you can concatenate them to make your output vector. This reduces, so this basically divides the memory requirements, because you're now just instead of calculating matrix, a lambda matrix for each of them. You just calculate one every age. So in the end, if you see here you can reduce the time requirements, but this age, as we will see in the results, it also affects the representational power. So you may not want to do this a lot. But here you can see that you took the batch out of the space requirement. So where n and m appear, which is the big space bottleneck, the batch doesn't appear. And where the batch appears, the n and m doesn't appear. And this is what's really important about this paper, is that they can actually reduce drastically the space required in memory to do these these operations. Cool. Is that clear?
Yes.
Yeah. No. Cool. Okay. So just real quick before we go into the results, I'm going to hop into the appendix, and just very quickly, what they do is so they test how these Lambda layers work, and they work pretty well. But they also test what they call the Lambda ResNet. And a Lambda ResNet, so this is a ResNet 50. So when they call a Lambda ResNet 50 is they change, so they substitute parts of these convolutional kernels by Lambda layers and keep the other convolutional kernels. So they do several tests where they say, well, let's do all Lambda layers, and then substituting convolutions by Lambdas, and they see the benefits in throughput. Cool. Okay, that's about it. So that's the whole. So before we go into the results, that's the whole juice of the paper. Are there any questions about it? Is there anything that maybe is not clear?
Maybe the training. How do they train it? It's so what is the thing that is actually parameterized in doing the training?
So they parameterize these weights are the learnable weights. So you have these learnable weights, and there is going to be something here as well. Sorry, in the softmax, there's going to be a linear transformation as well.
Mm. So it's really from the number of parameters pretty much the same as the self-attention, just the order of operations is slightly different.
No, so there are a lot less parameters, and they also have the because they use they get away with using smaller matrices, and these encodings are also learned. They're also learnable.
Yeah.
Did you say that the code for this was available, or was is it different code for that is available?
So they say in the paper that they will make the code available after publication. This guy, funny story. So in the video about Lambda Networks, Philip Wang, that's the guy who wrote this. So just funny comment. So yeah, this is just an implementation of the Lambda layer. The people from this paper said that they would make the code available.
Great, thanks.
Yeah, no worries. Okay, so yeah, so I guess the big question is, how does this stack up against state of the art? And well, so first they compare on ImageNet, and so the main, I guess the main result is that indeed they achieve better performance than what was the state of the art, and also with the self-attention mechanisms. So these are local self-attention and so on. Yeah, and they achieve better performance, but in the number of parameters, they are much, so they get away with much smaller number of parameters. So what we see is that they not only get away with higher performance, but they also have a higher throughput in using Lambda layers than what was the state of the art at the moment. Well, than what is the state of the art still. Even if you use global self-attention, which is doing this bit, but making C equal to X, they can't even get a throughput. So they run out of memory in 8 TPU v3 cores. They don't say how much memory there was in there, but you can see that they can get a much larger throughput. And yeah, so and the other interesting result is this plot here. And what we're seeing here is, so how long it takes to do training for a different number of image sizes, I believe. Yeah, depth and image size. So depth and image size. And what is your accuracy? So these are, yeah, so these are the previous state-of-the-art efficient nets. And you also have the rest nets. And they show that they are not only, so that they are they have higher accuracy and they are further left in the training latency, which means that they can be trained a lot faster. And if you, yeah, they also go in Cocoa and show that they also have better performance there. That is not surprising. But if you go to the appendix, you can also see the ablation study that they did. And I am a big fan of ablation studies because they actually managed to show that so the impact of your inner dimension. So this is the inner dimension of your model. Obviously, you want to have as many dimensions as possible, but also they show that this sort of lambda batching, you don't want it to be too small because you lose in performance. But also, if you start batching too much, you also lose in performance. So what seems to be an ideal setting is something around here. So 16 inner dimensions, which when you think about it is very small. So these matrices actually become quite manageable. And you have 16 million parameters, which when you compare it to a transformer, which has hundreds of millions of parameters, it's quite impressive. And the other interesting result is these lambda rest nets. You can see, depending on where you exchange the lambda functions, you have, of course, different throughput results. And in particular, you can see that if you substitute the first layers, so if you substitute these first blocks with lambda layers, you get much worse performance. And the intuition, or well, the justification is that, well, if you put a lambda layer here, your outer dimension becomes very large because it becomes the dimension of your input image. But the rest nets, they have the image size here. So actually, the later you put in your lambda nets, this outer dimension becomes smaller. So your lambda nets are actually faster. So yeah, so ideally you would start applying lambda nets from the last layer and then work your way up. And you can see that here it seems to be a good compromise. So do 2 convolutional stacks. I guess they're not just layers, but they're stacks, and then do 2 lambda layers. And this lambda ResNet architecture seems to be very good, or at least they show that it's good throughput and accuracy wise. Okay, so those are the results that they present. We are going to have the benefit of seeing 2 papers that are submitted to the same conference, and we can compare them against each other. So these are the ImageNet results from the Lambda layers. And if we look at the vision transformer, which is, if you remember, if you were not here a couple of weeks ago, the vision transformer basically adapts this pre-training and then fine-tuning NLP practice into image recognition. And well, they do it in batches of 16 by 16. So yeah, so we can, I think we have that recorded. But on ImageNet, they do 88.36% with their huge transformer at 2.5 TPU v3 days. Now, I'm not sure how TPU days stack up with this complexity, but you can see that the performance is a lot better. So we have an extra 10% performance in ImageNet, which is definitely not negligible. So I guess the main question here is going to become, do you have the time and resources to use transformers, or would you prefer a drop in accuracy but use Lambda networks? So that's it for me. Does anyone else have comments about the paper? Questions?
I would ask one question, because
Yes.
we have also seen attempts to make attention and transformers more efficient with various tricks and methods.
Mm-hmm.
It would be interesting to see how much speed up Lambda gains when comparing with more efficient implementations of attention.
Mm-hmm.
I didn't see it in the paper, but did they talk about it at all? Or
yeah, so they, sorry, one moment. Yeah. So here so that the most, let's call, efficient implementations of attention are these local relative self-attention, where they reduce the size of the attention mask that they have to compute. Other implementations of transformers like Albert and so on, they are more memory efficient, but they still have a ton of parameters, which means that they still require a very long time to train, because these networks. I lost the table. Yeah, so even like for example, DistillBERT, it requires you to train a bigger version of BERT first, and DistillBERT still has something like 30 million parameters. So it is still going to be slower to train than these Lambda layers, just because of the sheer number of parameters that they require.
yeah, that makes sense. Thanks.
No worries.
I'm curious to see. Oh, sorry, go ahead.
I was going to ask, what was the stopping condition? If they had continued to train for as long as the transformer would have taken, would they have continued to see a gradual improvement in performance, or did they stop early?
I didn't check all the training conditions, but I imagine they trained it as much as they could.
Yeah, normally, if they gained comparable results by training for longer, they would show these results. Right? They would say, let's train for fixed amount of time and then see which one gets better results. That's my guess.
Yeah.
Yeah, they mentioned that they train everything for 250 epochs, which is related to my comment/question, which is, are these Lambda networks, like if we keep adding more data, as in the other paper that you mentioned, Carlos, the one with the 16 by 16 image matches, that paper, they keep adding data, and they show that the transformer architecture is very good to still keep learning, and it has like 10% extra accuracy. So my question is, are these Lambda networks also scalable into those 88% ImageNet accuracies? But I don't think we have enough information to answer this question, but it would be interesting to know.
Mm-hmm. Yeah, I guess that is an interesting question. So yeah, that I think that one of the very interesting things about transformers is that they showed that they had to stop gaining accuracy because they don't have the resources, right? Like they have a very nice plot where they show, yeah, this is as much as we could do with the training budget that we had. But if we had more training budget, it seems like we would have continued improving. They don't do that analysis here, but I think that there's a big issue here, which is that they rely a lot on this locality to they rely a lot on this locality assumption to make their networks more efficient, which the vision transformer doesn't. So the vision transformer just sort of splits the whole space, but it's still a global attention mask. So I honestly don't think that Lambda layers have as much representational power as transformers, but they are an interesting alternative, I have to say.
Interesting.
Okay. Are there any more questions, comments? Okay, cool. So then thanks everyone for attending. And as usual, if you have a paper that you would like to present or that you would be interested in having a discussion about, please do get in touch with us. You can find all of our contact information in nplan.io. And we have been speaking about transformers and sort of related for a while. So do let us know in the poll, which seems like you don't want to change the topic. So we can try to keep looking for papers for transformers. But if there's another topic that you would like covered, please do let us know. We tend to choose papers that we're interested in, but we would be interested in seeing what you guys are interested in as well. So please do let us know. And yeah, see you next week. Thank you very much.
Thank you
very much. It was very good.
Yeah, very good.
Thank you, Carlos. Bye-bye.